Hello, everyone, and welcome back to your channel of Basic Engineering. What we are going to do today is analyze what we call distributed loads. Okay, what is the distributed load? Distributed load is load that is distributed over a beam or something, maybe due to snow that is uh, that fell on a roof or something, but it's not a load that is, for example, the weight of a beam or something. It has different heights, okay? Or if you are building a wall and the wall has that shape, so it's not really distributed uniformly. And the idea is when we try to find the reactions at the support, you want to have an equivalent load that is concentrated. So I want to replace those with just simple loads that we see over regular beams that we analyze. So we learn how to do that here. And basically, I would draw your attention to my other channel of uh, mathematics or math made easy, where I discussed the topic of centroids, because that's exactly what we are going to deal with here. There, if you have a different shapes, you learn how to find the x coordinate and the y coordinates um, of the plates or the shapes that you have, and find the centroid. Here, it's half a centroid problem because I'm not going to tell you how high is the centroid because I don't care. I need to know I'm going to replace this whole like shape with a single load, and I want to know where to place it. So I need to find the x coordinate of that centroid. I'm going to assume this is my x-axis, this is my y-axis, but I don't care about the y, okay? I don't care about the y. I only need the x. So I need to find x bar of that shape. Notice this shape is a load, not an area like what we discussed there. However, I can divide it into many shapes, right? But the easiest way to do, since we learned there how to find the centroid of a rectangle, a triangle, half a circle, second degree parabola, whatever the case might be, we divide that into these simple shapes. Of course, here I can see a straight line going up, so that is lending itself to a triangle. So if I draw this line, say in pink or whatever this color is, I have created an area that I'm going to call area number 1. And then I see here a trapezoid. We don't know how to find the centroid of a trapezoid easily. However, I can also divide that into a rectangle and a triangle on top of it, right? See that? So that is area number 2 or load number 2. And finally, I have load number 3. That is the top triangle here. I'm going to do it in, color it in blue. And like, again, as I said, if you already know how to find the centroids, then you don't need that session. But if you don't, I urge you to check my other channel, as I said first. So here we are going, usually I say shape. So yeah, shape, we can call it shape. We still have 3 shapes, so I'm going to say 1, 2, and 3. There I used to say area, but here I'm going to say the weight, because the weight here is an area. And then I'm going to say X bar and My. I don't need Y bar and and mx. So it's really a simpler problem of centroid. That should be a short session because it's really a repeat of what we did before. So I need to find the weight of each of these three shapes. The triangle has a base of 12 feet and a height of 800 pounds per foot, meaning that is zero here and it increases linearly until it becomes 800 pounds per foot. So if I multiply to find the area, I'm going to multiply 1/2 base times height. The base is foot, the height is pound per foot. So when you multiply them, you get the area in pound. And that's exactly what we want. 1/2 times 12 is 6. 6 times 800 is 4,800 pounds. Now, how about this rectangle? The base is 9, the height is 500, right? So it's 4,500 pounds. And finally, the triangle is 1/2 base times height. 1/2. The base is 9, but what is the height? Again, unfortunately, many students would say 800, but no, it's not 800. The height of the triangle starts from here, which is 500, up to there, which is 800. So it's only 300. But that's a common mistake. I've seen it too many times to be comfortable really with it. So 1/2 times 300 is 150, and 150 times 9 is 1350. Okay? And then you add them up and get the total weight. 0, 5, 8, and 8, 16, 10,650 pounds. So you say, this is from the previous session. Let me clear the screen and say, basically I said 0.5, 1/2 times 12 times 800 plus 9 times 500 plus 1/2 times 9 times 300. So you get 10,650 if you want to do it with a calculator. After that, we find the x bar, the centroid of a triangle. Remember, the centroid of a triangle, you locate the right angle and you calculate 1/3 of the base. So base over 3. If the base is 12, that distance is 4. Don't write 4. Again, I cannot overemphasize that. It's a very common error. Yes, this distance is 4. I'm not interested in that. I'm interested in the coordinate of that centroid that is here. How far is it from my origin? If that's a 4, then that definitely is an 8 because the total distance is 12. So I write 8 here. 8 times 48, that's 38400, right? Then here, the centroid is 4.5 from here. That distance is 4.5. But again, I'm not interested in that. I'm interested in how far from the y-axis it is. It is 12 plus 4.5, which is 16.5, right? So let's do that. Let's do, first of all, 4,800 times 8, and then 4,500 times 16.5. We get 74,250. And finally, I have another triangle that is, its base is 9. So 1/3 of that is 3. That's not the centroid, the coordinate. That's not x bar. X bar is 12 plus 3 or 15. So 1350 times 15 is 2250. And then you add them up to get the total of the my. This guy plus this guy plus that guy. 132.9. Okay? And finally, you say x bar, the centroid, equals my over the area, which in this case is the weight. So you're going to divide that by 10,650, and you get 12 point roughly 48 feet, 12 and a half feet. You always ask yourself, does it make sense? 12 is here. So if this part and this part are exactly the same shape, meaning if that was 12 and you get a triangle, I would get X bar at exactly as 12. It seems like this, even though it's shorter, but it's heavier than the left-hand side. So in order to get the centroid, you move slightly to the right. In fact, we only moved less than half a foot, I'm sorry, less than half a foot to the right. But that's basically how easy it is. So now I'm going to say I have my beam. Here is point A. I have a pin at point A. I have a roller at point B. That distance is 12 and that distance is 9. So let's extend it a little bit. And we say that I can replace all of these loads with a single load here that is 12.48 feet away from point A with a magnitude of 10,650 pounds. These two would be equivalent. Please be careful. It's the most important thing. It's equivalent for finding the reactions. Meaning, instead of trying to find, the moment about point A of all these loads, I only can say, suppose I want to find the moment, I'm sorry, the reaction at B or B, I would say 10,650, which is rotating clockwise, so it's negative, times 1248. And then I have a reaction going up, going counterclockwise, plus 12 by equals 0, and that allows me to find by. Summation of the forces in the y, I get ax. I'm sorry, ay. And there is no horizontal force, so ax is 0. But it allows me to easily find the reactions at the support. Please, that's all what I needed for. So I only needed that to find the reactions. If you are taking an advanced course, say in structural analysis or strength of material, and you want to find the shear force or the bending moment diagram, I'm not going to use that. Of course not. That would be ridiculous. It's not correct. Again, for the last time, transforming the distributed load into an equivalent single concentrated load. In fact, I usually to do the three steps, I have a load here. Originally, I replaced this with the load of 4,800, 8 feet away, and 4,500, 16 and a half feet away, and then 1,350, 15 feet away. So these three and then I combine them into one just for simplicity. I could have used these three and I would have gotten the same magnitude for By. But that's it. Once I find the reactions, I go back to the original thing and then see how, when you learn it, how you find the other like type of forces like shearing forces and bending moment diagrams and normal forces if there are normal forces. And that allows you for a step later to find the stresses in the member. So that allows you to pick a corresponding cross section, maybe a different material, maybe a different shape of the cross section. All of this you would learn in more advanced courses. But for now, I just wanted you to learn how to replace distributed loads with a concentrated load because it may appear, or it may you may encounter that in some structures. So thanks for your time and hope to see you soon. Bye.